Is part 3 of our trapezoid rule demonstration. So remember that last time we gave the theoretical error bound, and I'll just scroll back up to it here, of 1/12 times the second derivative bound times the cube of the length of the interval divided by the square of the number of subdivisions. So we're now going to just look at that for our test integration. So let's see. Um, for the test integration, the function is sine. So remember our m value is 1.0. That's the lowest m that will bound the absolute value of sine on the interval of integration. So I can compute error bound data for various values of subdivisions. And I can also compute the actual performance of the integrator. Now, we're going to make a log-log plot of this. So we're plotting the number of subdivisions as a power of 10. We're plotting the log base 10 of the error bound and of the error. So let's just take a look at that plot now. Okay, so I'll make this window a little bigger and delete the palette because we won't need it right now. So you can see that with 10 subdivisions, here's the error bound, here's the actual error. With 10 to the 5th subdivisions, what's that, 100,000, the error is much smaller. It's down around 10 to the minus 10. And again, of course, as you'd expect, the actual error is less than the error bound. Now, I've said that this is a hard bound, and I mean it. But of course, there's a very small asterisk on that, because when we say it's a hard error bound, we mean that the actual sum of those function values differs from the actual integral by less than this. It does not mean that the floating point computation of the sum in the trapezoid rule is closer to the actual integral than this. It's still possible for round-off error in the computation of the sum to lead to a larger error than this approximation error bound. It's just rare because summing is a lot better in terms of round-off error than the kind of differencing we were doing for numerical differentiation. So I just wanted to clarify that point from last time. Okay, so we can see that the results are actually quite close. The trapezoid rule comes pretty close to the actual theoretical error bound. So let's try another example. So in the homework, you're going to try the trapezoid rule with different test integrals and look at the error bound. And you'll see for most of the integrals that you try that the error bound is pretty tight. So here's an example where the error bound is not so tight. So let's take the integral of e to the sine x. Okay, so again, I type this in a code box, so it's just going to evaluate the integral. Mathematica tells us that the answer is in terms of this special function called the Bessel I function, evaluated at a certain value. And Mathematica can evaluate as many digits of the Bessel I function as we'd like it to. So there's 20 and 200 digits of the Bessel I function. So we know, at least in a we can compute it as well as we want sense, the answer to this integration problem. Now the function is certainly a perfectly reasonable looking function. Let's just take a look. So plot capital E to the sine x x0 for pi. And you see that, okay, it's not quite as regular as the sine function itself, but it's certainly perfectly reasonable. Now, we can compute the second derivative symbolically. Notice that I used Mathematicas D to get the derivative, and I used full simplify to try to write it as simply as possible. And you get e to the sine x times cos squared minus sine. If there was a nice trig identity that would simplify this further, full simplify probably would have found it. So we now need an upper bound on the absolute value. Now there's a lot of ways you can do this by thinking about sine and cosine, by thinking about e to the sine x. But really at this point in your life, it's okay to use Mathematica and just type maximize. So it's perfectly happy to do this. And note the syntax here. I wrote the thing that you're supposed to maximize, the comma, the constraints on x, and then I had to tell it the variable. And it's happy to tell you that the maximum absolute value of the second derivative is e, and it occurs, for instance, at x equals pi over 2. So I'm just going to put e in as the value of m, and I'm going to compute error-bound data, and I'm going to compute I'm going to plot the error floor 10 to the minus 16th, and I'm going to compute the trapezoid rule performance directly. I'm going to do all of this in machine arithmetic. So I get some data. I get some data for the least possible error, get some data for the trapezoid rule, and I plot all these guys together. Okay, now check this out, right? Because it's really crazy looking. What we see is this is really close to 2 intervals or something. It's 10 to the 0.2, ceiling of 10 to the 0.2 intervals. So at first, there's this kind of up and down. Now it's always less than the theoretical error bound. This is good. Then it drops precipitously, climbs up and drops again. And by something like 20 intervals, it's already at like 10 to the minus 15. So it's got 15 digits correct. And then it just wobbles around having 15 digits correct. This is already pretty much the best error you're going to get. And of course, it doesn't improve by adding more intervals. So super weird, right? Two things to notice. One of them is that if you were just following the error bound or computing as you did above, you would have concluded that you needed something like 100 million intervals to get out to 10 to the minus 12 or something, whereas you actually need like 20. So whatever's going on here, it's advantageous to know when it happens so you can capitalize on it. So let's take a look more clearly in the range between, say, 10 and 150 intervals. So this time we'll make a log plot rather than a log-log plot. So we'll display the actual number of intervals against the log of the error. So this will take just a few minutes to do because what I've done is I've asked Mathematica to do it in absurd precision. So in a maximum of 20,000 digits of precision and evaluating things numerically in 2,500 digits. I just picked these numbers to be big. It was fast enough anyway. Okay, So here we go. This is really interesting, right? So notice first, there are no round-off error effects here, simply because we did the computation in such an absurdly high precision that round-off error is much smaller than any of the errors we're talking about here. So the error bound is up here. You can see it's very gradually decreasing. But the actual error, this is something like 30 digits right, 40 digits right, 60 digits right. So by the time you get down to 49 intervals, you get like 180 correct digits. Um, but 48 intervals only gives you something like 30 correct digits. 50 intervals gives you like 80 correct digits. So there's obviously this weirdo kind of mod 3 thing going on with the number of intervals. Um, and there's also just a really unexpectedly high accuracy. So uh, just to look at it with you, um, here are the first 185 digits of the exact answer, 4 pi times the Bessel function evaluated at a certain place. And here are the first 185 digits of the trapezoid rule for this function, evaluated with 47 intervals. And you can see that it matches perfectly right up to the 746 here. It's 7466 in the right answer, 7465 uh, in the um, in the trapezoid rule approximation. So we're getting an absolutely crazy amount of accuracy. Well, why? Um, there should be some kind of theory which explains this, and we'll get to that in about a class and a half.